Welcome back to the lecture Multimediale Werkzeuge. This part is about representation of the DCT as a filter bank. So first, as I mentioned, for coding we need to make this assumption of having a certain viewing distance and a certain playback size of our image or video, which then results in a certain viewing angle for the eye. This also applies to the original image or video to a certain extent, since the eye must be far enough away so that it can no longer distinguish individual pixels. So here's an example where this is not working. When you have a low resolution image like 3 megapixels and you print it out as a poster on A0 paper, then it looks more like a mosaic where individual pixels are rather large and not like a continuous image. So this shows it needs to fit the number of pixels and the display size. Yeah, question. What if the edge length of the image cannot be divided by 8 like we need for the DCT? The answer is fill it with zeros such that it can be divided by 8, or better mirror the end for better frequency response, or simply cut off the additional pixels. So there are several ways and it doesn't really matter so much because it's just the edges. Okay, so then to the representation of the DCT as a bank of filters, a filter bank. So we saw we apply our DCT to blocks of 8 by 8 pixels, and it turns out this can be also interpreted as a bank of filters, which is the what the DCT is doing with its subbands. Right? For each subband of the DCT we get one filter, and since we have this blockwise representation, this corresponds to a downsampling by a factor of 8. Right? Because without this downsampling by 8, for each subband we would have exactly as many output samples as we would have input samples, which means the subband images would have the original size. And we already saw that the subband images have a size which is 1/8 along the edges. So that means we have a downsampling in the processing, right? By just processing blocks of size 8 by 8, implicitly in this filter bank representation, this means a downsampling by a factor of 8. Right? So 8 samples come in, 8 samples come out, and then only one sample is left here. For instance, the DC value. So all the rest is basically ignored. This is depicted here. The dots are the ignored samples, and then these samples are passed. Right, and then for each subband we have one of those filters, and as we know, filtering means convolution, so we convolve the input sequence or pixels with a filter impulse response. And this is slightly different than what we do for the DCT transform. We remember we have x times cosine, and for convolution we have x times the impulse response, and then we have the indices of our x and our n impulse response running reverse, and in the transform it's not reversed, so that's why here we get the impulse responses by just mirroring the columns. So the effect can be seen as a set of 8 filters, the effect of applying the DCT. Each of these 8 filters has an impulse response corresponding to the 8 mirrored columns. So when we look at the DCT transform matrix, each column represents the impulse response of one subband, but in a mirrored way. So we need to read out the impulse response from bottom to top. Right? So easy enough. So these 8 filters filter our signal, the convolution with the signal. After filtering, a downsampling is performed by this factor of 8, which means only every 8th value of the filtered signal is left. And in this way the total number of values remains constant, as we saw. We just replace a block of 8 by 8 pixels by a block of 8 by 8 frequency components. Yeah, and this is also what we saw in the pictures of the subband signals. All the 8 by 8 subband pictures fit into the same size of the image as before. Yeah, important point here, the shown transform, I should call it transform, the DCT and the representation by filter banks are equivalent. They are only mathematically different mathematical representations. So it should be different. The representation as transform is usually more favorable for the implementation because often we have fast transforms implementations for it. The representation as a filter bank is more favorable for the design for instance, image processing or coding algorithms. Yeah. So we have one filter for one subband image. So you can think of each subband image being generated by one subband filter and subsequent downsampling. This means that an appropriate filter is needed for each of the 8 by 8 images of the subbands, or altogether 64 filters. According to the 64 pictures of the subbands shown in the previous examples. So then there should be a comma. Yeah, so we have applied the DCT separately horizontally and vertically to the image, and this can be seen here in this block diagram. Here we have to the left our original image, and then we apply our 8 filters, first horizontally, right, and yeah, here we have the filters, horizontal filters, then the downsamplers. So here we have the horizontal subbands, horizontal Teilbänder, this is still German. And then we take the result and apply the vertical filters, right? Filter 1, filter 0 to 7, and do the downsampling vertically. So here in the first stage we do the downsampling horizontally, we would get a narrow image. And here we do the downsampling vertically, we get a vertically reduced image. And in the end, we have both dimensions covered. And this is then the result. Again, the same, right? So we see the result is indeed the same as with the transform. It's just a different representation, or a different viewpoint, you could say. Yeah. So in this way, we have a cascade of horizontal and vertical filters for horizontal and vertical frequencies, and resulting in subband images. And each of those filters, they filter out certain properties from the image, right? As we saw, horizontal edges, vertical edges, diagonal edges, and that also makes this viewpoint interesting, this representation as filter bank. Because we can interpret it and we can also modify it now. So first, if we want to modify it, we also need a decoder, as also in compression. So for the filter bank representation we have also reconstruction, and that's the synthesis filter bank. Right? So the synthesis filter bank would be used in the decoder. The image is reconstructed from the subbands, first using upsampling as opposed to downsampling to resize the subband images back to the original size, and then filtering, which can be interpreted as interpolation. And this can also be seen by using the bandpass Nyquist theorem. If we have 1/n of the bandwidth, we can represent a signal by 1/n of the sampling rate and still be able to reconstruct it. So this can be seen here. We have the upsampler here for the synthesis filter bank in the decoding side, And this upsampling consists of taking each sample and adding 7 zeros after each sample, if you want to upsample by 8. Right, so this reconstructs the original image size then. And then this is followed by, again, filtering. So here, synthesis filter 0 to 7. And since the complete image consists of all frequencies, we need to add all frequencies up to get the reconstructed picture. Right, so this is the synthesis filter bank, and again we need to do it for each dimension, horizontally and vertically. Yeah, and perfect reconstruction is desired if we don't make any changes in between. We want to have the reconstructed image identical to the original image. And for the DCT filter bank, this is easy because we can also represent it by this square matrix multiplication, and since it's a square matrix, it's invertible. Right? Not every square matrix is invertible, but the DCT is. So that can be used to obtain the synthesis filter bank for perfect reconstruction. We just take the inverse matrix here and look at the inverse matrix to get the impulse responses for the synthesis filter bank. Right. So here again is the forward transform of the DCT. No, this is the inverse transform. Again, here we have the cosine terms. And these cosine terms here are now obtained from the inverse matrix. Right. We can just rewrite the inverse matrix multiplication using this sum formulation with this special factor AK here. Yeah, so that means we now have a decoder, the synthesis filter bank, which reconstructs from the subbands, and we have an encoder, which is the analysis filter bank, which does the decomposition into subbands. So maybe I should call this filter bank. And here we have the analysis filter bank. Right. So the complete chain would then be, we have the original going into the encoder or the analysis, and then we have the synthesis or the decoder, and then we have the reconstructed image. And now we can also do modifications of the subbands. Right. So I should call this decomposing. Decomposing the image into subbands in this chain. We also have the possibility of modifying subbands in this chain, right? And that makes it interesting, because then we can remove or enhance certain properties. So here's an example. We only keep subband 0, 0. So there should be comma because it's two indices, which means DC, and the remaining subbands are set to 0, right? Yeah, and the result for the reconstructed image is then that it looks low pass filtered with less delay, less detail, right? Because DC, remember, just contains the average brightness over each block, and all the details are contained in the higher subbands. And if we just remove those higher subbands, then all what's left is the average brightness over each block. And this is how the resulting image then looks like. So here you can see this basically looks like the small DC image, but just larger, right? So this has the size of the original image, but you can see it loses all the detail. It looks blurry basically, and we can actually zoom into it, and then we can see that it actually looks blocky when we zoom far enough. So let's see. Yeah, so here you can clearly see now it's the blocks. So these are the 8x8 blocks. So basically this image now consists of pixels which have equal brightness over each 8x8 block. All the details are missing. Okay. So here as a comparison is the original. So this contains much more detail, which you also can see when you zoom in. So this zooming in is always a good trick to compare images. But when you do actually lossy compression, you assume that you don't zoom in, right? That's part of the assumption. Yeah, so zooming in is kind of like cheating for lossy compression, but it helps to see the differences. So here you can see it's no longer those 8x8 blocks, and now we have much more detail because this is the original, right? So yeah, so this is what I just mentioned. It consists of pixel blocks of DCT size 8x8 pixels, and they have the same pixels. Yeah, pixel blocks of constant brightness. Oh, maybe I should just call this of 8x8 pixel blocks, make it a little shorter. Okay. Yeah, it contains abrupt transitions between the 8x8 blocks. So in that sense, it contains edges. So it doesn't look so low pass-like with gradual transitions as you would expect from a low pass filter, but it still has those edges at the boundaries of the block. So we have blocking artifacts, and that's coming from the DCT, from those 8x8 blocks. And yeah, this is an important drawback of this transform. The artifacts look unnatural. You have edges where in the original image there were no edges. So next example here, instead of just keeping DC, we keep the 4 lowest subbands. And the result indeed looks less blurry. So here we can see this almost looks like the original, even though we just kept just 4 subbands, 4 out of the 64, right? So when you compare this without zooming into the original, here's the original, right? And look at the branches, they're nice sharp in the original. And now here, look at the branches, they're still quite sharp. So it's really good, even though we have just 4 out of 64 subbands here. And I can also zoom in to see some differences, to be able to see differences. And it's actually hard to see. So here it's a little bit less sharp here in the branches because the higher frequencies are missing. So when you compare here the branches into the original, they look slightly less sharp, but it's still quite good. Right. So here you can see the used subbands. We took DC and then the surrounding higher frequency subbands, 4 out of 64. So the image indeed looks sharper, but still has some blocking artifacts, which can also be seen after zooming in. But you really need to look closely to see the differences. So this also shows why this is a good approach for compression, because we just took 4 out of 64, which means we have 1/16 of the original data for reconstructing the image. And it still looks quite good. Yeah, next example, we keep all subbands except DC. So remember, DC contains the most important coefficients, right? So the average brightness of each pixel, of each block by 8 by 8. So this is what you get. So here we have now only the higher frequencies, which means only the brightness changes over each block, not the average brightness in each block. And this is what you get. So basically, you keep the edges, right? You don't keep the brightness of the sky or the snow surfaces. You only keep the edges. Say here you have the edges of the window, here you have the edge of the roof, then the many details from the trees, and then the roads here in the distance. But you can see here the snowy surface looks black, as the same as the sky looks black, because there are no details. Or here the numbers from the date, you can see the edges of them. So this almost looks like an artistic drawing. If you have a black paper and you draw with a white pen, this is what you would get in a drawing. So it's almost something artistic. Yeah, so only the edges in the image remain, which means the high spatial frequencies. Right? And this can also be a tool for extracting edges. Yeah, next example, all subbands except DC are amplified, so by a factor of 2. Right? So this enhances the edges in the image by this factor. So basically this is edge enhancement, and this is the result. Right? And this is now actually looks even sharper than the original. So here the edges are even more pronounced when you compare it to the original. Going back to the original, there's the original. This was the original, right? Here's the original. Look at those ways, and here the edge of the trees, and then compare it now to this one here. So here those ways and those branches, they even now look more crisp, more sharp than the original. And this is actually what's indeed used for sharpening an image. So when you have an image tool like Photoshop or GIMP, then you have sharpening tools, and that's basically what they do. They amplify higher spatial frequencies to make edges look sharper. And when we zoom in, we can see how it actually is doing this increased sharpness. So for instance, when you look at this way here, you can see at the edge the surrounding gray area becomes more bright, and the edge and the darker part becomes more dark. So in the vicinity of an edge, it increases the contrast basically. So here you can see this white line here, which makes the edge appear more sharp. And this white line here at this edge was not there in the original, but is the result of amplifying the higher frequencies, the higher spatial frequencies. So again, it's a useful tool for improving images or give it some artistic effect. Okay, yeah, so that's it for today, and I hope I left you with a little inspiration for own experiments for image processing and enhancement or artistic effects. And then, yeah, thanks for your attention, and see you next time.